Hello, welcome to this clip going through the rate determining step, which is used to construct the rate equation when we're looking at rates and orders of reaction. If we look at a simple example, an imaginary reaction A12B, obviously you've got 1 mole of A and 2 moles of B present in the overall equation. But the problem with an overall equation is it's just that. It doesn't actually include the steps that might be present in the mechanism, or which of the steps is the slowest. So if we assume that the reaction proceeds by a series of steps, and one of them is slower than all the others, obviously it's this step that determines how quickly the whole reaction actually goes. So the slowest step is called the rate determining step. So as a result, the influence of the rate determining step is absolutely pivotal to the speed of the whole reaction, so therefore the rate equation will only contain the reactants for the slowest step and none of the others. So the ratio of the orders that you find in the rate equation will be the same as the ratio of the moles of each of those species in the rate determining step. And this is really important to seeing the link between the rate determining step and the rate equation. So we can look at an example, nitrogen dioxide reacting with carbon monoxide. We can put in the overall equation, and we can take experiments between changing the concentration of each reactant and the effect on the reaction rate, which gives initial rate data that suggests the reaction is second order with respect to nitrogen dioxide and zero order with respect to carbon monoxide. So in terms of what the order means, it's the power to which the concentration term is raised in the rate equation. So if it's second order with respect to a reactant, if that reactant is doubled in concentration, the rate will increase by 4. If it's zero order with respect to a reactant, then there'll be no effect on the rate of reaction for that particular reactant. So in the case of carbon monoxide, there'll be no effect at all, so it's zero order. So we'll be able to work out from this that the rate equation is rate equals K times the concentration of NO2 squared. And the concentration term is raised to the power of 2 because that means it's second order. And we can also deduce from this that there's 2 moles of NO2 present in the rate determining step. So the other steps must be fast steps, and if you add up all the steps together and cancel out as you go, you must end up with the overall equation. So let's now have a look at how we might put together the mechanism as a result. So we don't know how many steps there are, so let's not make too much work for ourselves and think about maybe having 2 steps. So we know that one of the steps has 2 moles of NO2, or 2 molecules of NO2 as reactants. So we know that step 1 is going to be the slow step, or the rate determining step, and we know that step 2 is going to be the fast step. We also know that overall, with all cancelling taken into account and adding up, you have to end up with the overall equation as shown. So we know that carbon monoxide is a reactant. We can see that from the overall equation. So therefore we have to put it in somewhere, so we need to put it in step 2. So looking at the second step still, carbon dioxide must be a product there because it can't be a product in the first step because there's no carbon in the reactants, but it's in the overall equation, so it must be a product in the second step. Now there's only one nitrogen containing product in the overall equation, so that's nitrogen monoxide. So one of the NO2 molecules needs to turn into that nitrogen monoxide molecule. So to do that, it's got to lose an oxygen, gain an oxygen from the other one. So one nitrogen dioxide takes an oxygen from the other nitrogen dioxide to make NO3. Now NO3 is an unusual intermediate, and at the same time carbon monoxide has to become CO2, so the NO3 doesn't hang around for long. It loses an oxygen, gives it to the carbon monoxide to produce CO2, and that now gives us nitrogen dioxide as a product in step 2. So cancelling will start to reveal the overall equation. So it's worth summing up by having a look at some of the reasons behind why the slow step is actually slow. You'll generally find that slow steps involve breaking bonds, which is an endothermic process which requires energy. And in this case, a bond's being broken in stable species, NO2. In step 2, bonds are being made, which is exothermic, and therefore this tends to happen more easily. And in addition, in this case, an unstable intermediate, NO3, is being used up. So to summarize, we can say that slow steps tend to use up energy by bond breaking, and fast steps tend to give out energy by bond making. So it is worth sort of linking this idea to the thermodynamics of what's going on as well. Okay, so that takes us to the end of this clip. Hopefully it's been reasonably useful in allowing you to see some of the ways in which you can think through how to construct a mechanism using the rate determining step and the rate equation. Okay, so until next time, thanks for listening and see you soon.